Hello, hello. It is a delight to see all of you here. Welcome back to ArmanisMath. This is lecture number 14, and today we're going to discuss the graph of sine. The graph of the sine function. What a journey. So I'm going to start this journey by welcoming all of you here and expecting to see good things today, all right? So get ready, get your notebooks ready, and let's get started. As we always do, we start with the warm-up. So here is the warm-up for the day. I've got a couple sine values, and then we've got the graph of y equals x squared, which is quadratic. If you guys recall, from maybe 5 years ago or something, like when you were in kindergarten. Did you guys do quadratic in kindergarten? Oh, I think you did. Good job. Wow, I'm happy for you. Okay. So as always, I'm gonna give you a timer here. Probably a couple minutes here, and for those who are later on watching or studying using the video. Hello. Yeah, hello. Oh wow, I've got two of them here. Okay, just one of them is what I need. And for those of you who are watching this after the fact, I'll probably pause. I'm not going to wait for 2 minutes, but just pause and then go with that, okay? But it's important to do the warm-up. It just gets your mind in the game. I do watch comments at the same time that we're here. Hello there. Hello there. Interesting and unique name. Good to see you here. Here we go. We got some answers here. So sine pi over 6. Pi over 6 is, if I remember from the unit circle, this is taking the 180 divided by 6. That's a 30, so sine 30 is what we're talking about. And I've got some answer in the chat. Sine 30 is 1/2. Sine 30 is 1/2. Sine pi over 4. Pi over 4. And I see also some answers there. Pi over 4. Excuse me. Not sure what's going on with this cough here. Pi over 4 is 45, and sine of 45 is square root of 2 over 2. Same thing with cosine. Graph of the y equals x squared. So I'm gonna just give myself x and y coordinates here. Polar Cartesian coordinates, I should say. And to graph y equals x squared, I mean, you could obviously come up with your own table if you like. I would probably put a table here. Excuse me. Maybe put a table here and just put x and y. Put some values for x, and this is y. So if I put, let's say the easiest one is -2. 0, 2. So if I put -2 for x, -2x, -2 squared, that's going to be a positive, positive 4. 0 is 0, 2 is 4. So 0, 0 is here. And let's say this is 2, this is -2. So at 2, I'm going to go up here at 4. -4, I'll go up here at 4. And I should look something like that, okay? Something like that. This is y equals x squared. Y equals x minus 3 squared plus 2. So once again, if you recall, this would be the h. So this is h. This is the k. H is left and right. K is up and down. So k is up and down. H is left and right. H is always the opposite of the direction that you see because of the actual function has x minus h. Okay, so there's already h built in. So basically what you're going to do here is you move into the right 3 units. You move it up 2 units. Okay, and I could probably easily graph this by having y-axis. Give myself my room here. Having y-axis, having also x-axis. But I'm going to give myself my room, so I'm going to go down here. Okay, and to graph this, I'm going to go. I mean, you could definitely build yourself a table here and just go from there, or you could just by inspection, you say this is going to 3. So instead of starting at 0, 0 at the vertex, you go 1 and 2 and 3, and you're going up 1 and 2. So basically, your curve is going to be here. Your function is going to be here. You moved to the right 3, and you moved up 2. Okay, this is just a review of the graph of a quadratic function. Why are we doing this? I thought we're talking about sine. Obviously, there's a reason. That's why you put when you do the warm-up, get your brain ready for the actual concept. So you will be able to recognize and graph sine trigonometric function. Where in the whole world are we using this? Where is this used? Well, is one of many areas is the music, radio waves and sound waves. All these are composed of various frequencies and amplitude that actually can be described using the sine waves and the cosine waves. And so all these are examples of things that you could come up with. Can you think of another one? If you could, put that in the comments, please. Here's some vocab to get us started. What is a periodic function? Periodic function is a function that repeats exactly in irregular intervals called cycles. So this kind of function that we're looking at today, excuse me, which is a sine function, it does repeat itself in cyclical kind of ways. So it has a cycle. It goes from one point to the other point and then keeps repeating itself again. And these intervals are called cycles. The period is the length of this cycle. How long does it take for it to start and finish the wave? That's the period. The third thing is the amplitude. How high can it reach? How low could it go? Okay? So that's the amplitude, how high and how low. And by the way, the amplitude is a distance. So distance is always positive. Distance is always positive, and that's why we use the absolute value for that. Okay. Another thing is the frequency, which is measured in hertz, is the number of cycles in a given unit of time. So basically, once we're gonna, I think we could just take a quick example on this one towards the end, but the reciprocal, it's 1 over the period, is called the frequency, and it's measured in hertz. The person who discovered that or invented that. The phase shift is the horizontal translation of the periodic function. This is exactly what we just did with the quadratic function. Remember, we shifted that to the right 3 units, to the right 3 units. That's what they're talking about here, phase shift. Okay, so you take the wave and then you shift it to the right. What is a periodic function? So here's an example to the left of a periodic function. This is an example of a periodic function. You are looking at one right now. Something that repeats itself. So if you look closely here, this guy starts from here and then goes down. Let me change the color. It's going to be a little bit easier for you to see. I start here at the top at 1. I go down here and I go up here at 1. And then I start the cycle again. I go up here, I go down here, and then up here at 1. And I start the cycle again. Go down here, up here at 1, etc., etc., etc. By the way, you also could do it in both directions. Just like rotation, when you do clockwise, counterclockwise, same thing here. You could rotate this side and this side, and you keep going and going. So we call this as periodic function because it does repeat itself exactly in regular intervals. So this is one of them. This one is not, obviously, because this does not repeat itself. If you looked here, that does not repeat. Look at this. And then whoop, away. That's not repeating itself. So this is not a periodic function. So another example of a periodic function would be, let me show you this one here. Maybe I have a graph like this, and another one like that. Let's say, for example, that I'm going to start here. I'm going to start here. And I'm going to start from 0. So I'll start from 0, go up, then go down, and go up. Okay, I stopped here. And then I'm going to try this again. I'll go up, go down, go up. So you notice I did actually repeat myself. Right? Okay? That's why we call a periodic function. Something that repeats itself in regular intervals. Same amount of time. So from here to here, it takes the same amount of time to proceed. Okay, so it takes the same amount of time. This time here, this time here, this amount of time, yeah, is the same as this amount of time. Okay, and we call that periodic functions. Here's the first example. It says, identify if what you see is a periodic function, and then, if it is a periodic function, can you give us the period? How long does it take from it to start and finish? So the good thing about periodic functions, it doesn't matter where you start, as long as you have a starting point. For example, do you think this is periodic? This just to start initially, we have to answer a question. Is this periodic? Does this happen over and over and over again using the same pattern? Does the pattern repeat itself over and over and over and over and over? Can you help me with the comments? Apparently, the function I'm looking at here does repeat itself. It does repeat itself. That's not surprising, because I'm looking here and I see that it does repeat it. Look, if let's say I start here, different color for this guy. Start here. I go all the way up and down and then go all the way up. See that? I'm gonna start here. Over here. Okay, so I took all the way this distance here. See that curve? Guess what? You could repeat this wave again. And let's take not red, come on. Let's take black. So I could start from here and then go all the way here. See, I'm repeating myself. I am repeating myself. Start here. So obviously you look at this thing and you say, yes, it is a periodic function. It repeats itself. All right. So here's what we're after today. We need to graph the sine function. Interesting. How do you graph a sine function? Well, let's take it easy, okay? I was preparing this and I actually took a lot of time to prepare it, so hopefully it's gonna make sense the first time you see it. I wanted you to think of a couple, like a fun example. For example, you have a coin in your jeans and you forgot that, and then your mom took it or you took it and put it in the laundry, and here goes the dryer. Clink, 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 clink. And then you're thinking, okay, well, how do I graph that? If I were to graph this cling, cling, if I were to graph this cycle thing, how do I graph it? Obviously, if you take a pencil and then you want to graph it, so you're not gonna just go over the same circle again and again and again. That means you're gonna pierce the your paper, right? So there is actually a graph. There is a way to represent this rotation in math and this cyclical in terms of, in our case today, it's going to be the sine wave. So you're going to start the sine wave, and then you're going to see how would you represent this cyclical function. So first thing first, I want to start very easy, which is we need to observe the sine Okay, so we're going to look at every sign and observe that. So for example, here, down here, this is x and this, remember this is x and this is y. Y is the, does anybody remember what is y? Is the y the sine or cosine? Is the y the sine or cosine? In the chat or in the comments, is the y sine or is it the cosine? And that's the question. Is it or is it not? Thank you. It is the sine. It's the y. The y is the sine. So basically I'm looking here. I'm looking at 0. And I'm looking at 1/2. See that? It's like sine of 0 is 0. Sine of 30 is 1/2. Sine of 45 is this amount. While you're watching me do this, can you use your calculator to find us the value for square root of 2 over 2? And somebody else use the calculator to find us the value for square root of 3 over 2. So use a calculator to find the exact value. I shouldn't say exact, approximate, using a calculator. So find the approximate value for square root of 2 over 2, and somebody else for square root of 3 over 2. So look, if you observe exactly what I'm doing, I'm just circling the y's, because we want to graph the y function. So I'm just going to observe the y. 0, 1/2, that's a little bit bigger than 0. Square root of 2 over, I'm still waiting for you guys to find the square root of 2 over 2. Use the calculator, and square root of 3 over 2, and then 1. Okay, sine is 1. Okay. And then I see myself going less than 1. The square root of 3 over 2 is less than 1. Square root of 3 over 2. Interesting. And then square root of 2 over 2. And then 1/2. I'm decreasing. The amount is decreasing. The amount of sine is decreasing. And then I'm back to 0. What? Yep, that's what you do. And then let's go back again, and then just watch that. In the comment, I am still asking you if you could look at square root of 2 over 2 and give us the value in the comment here. And also square root of 3 over 2. I see one of you give me, thank you. I've got 0.7. I like that. Somebody find us. So I'm going to just actually thank you for, I'm going to put 0.7. About 0.7 here. And square root of 3 over 2. Somebody else find us that. So now I'm going to keep going with this with sine. So now I am to the -1. Negative. Oh, interesting. -1/2. A little bit bigger than -1/2. A little bit bigger than -1/2. And then I see myself looking at -1. All what I'm doing is just observing the value of my sine, sine of the angles. So now I look at negative again, and then negative, and then -1/2, and then oops, back to 0 again. Interesting. Did somebody find us what is the square root of 3 over 2? So just by inspecting here, I see myself, I'm repeating. Sometimes I go negative, sometimes I go up, and then I go down, and then back to 0, and I repeat myself again. Because if you want to rotate again, you're going to get the same values. 0, 1/2, square root of 2 over 2, square root of 3 over 2, which I'm still waiting for you two guys to give me some. Give me, please, square root of 3 over 2. Thank you. 0.866. Okay. So just keep that in mind as we work these problems, okay? So we just walked around the circle. We took a quick jog around the circle, and then we just look. So let's focus a little bit. We're going to zoom in a little bit now, okay? So let's say we just wanted the easy points, which is, to me, easy meaning the ones and zeros. So we're still going to graph the equals or f of x equals sine x. And let's do that. I have 0 degrees. At 0 degrees, my sine is 0. That's what I put here. At 90, sine is 1. And that's what I put here. At 180, the sine is 0. Interesting. Sine is 0 at 180. And at 270, the sine is -1. There's -1. At 360, or 2 pi, I go back to 0. So that's easy, right? So you go from your unit circle to the table, because knowing the table is going to help me plot and graph this kind of function. Well, what I did is looked at easy points, which has zeros and ones, and I just followed the pattern. Counterclockwise as always, right? Default counterclockwise. And I start from 0. 0 degrees has a sine of 0. 90 degrees has a sine of 1, etc. all the way when you go back to 360, which is 2 pi here. That's going to give you the 0. So how do you graph that? Well, take the points and graph it. What do you mean how you graph that? Just plot the points. Come on. This is the x-axis, which has our theta, or angle. The angle is the x-axis, okay? And the y is the value for the function. So this is the f of x, or the y, f of x, okay? F of x, or the y. Y lives here. Okay, so this is the y, and this is the x. Now, let's plot the points. If I put 0 degrees, remember, degrees are down here. This is theta. I have to go all the way to here. Here's a spot. Let me give myself more room. I need a spot here. And I have 90 here. I have 180. I have 270. And I have 360. Okay? Remember, I'm just going to go from the unit circle we went to the table. From the table, we're going to go to actually graph it. So at 0, I'm at 0. Well, that's not surprising. I'm here. Sine starts at 0. Sine starts at 0. 0, 0, that is, of the origin. And then at 90, I go all the way to 1. So if this is my maximum, or this is 1, this is negative 1. At 90, I go all the way up here. At 180, look at 180, or the pi, I go back to 0. At 270, I go to negative 1. At 360, I go to 0. One more time. At 0 degrees, because this x-axis has the degrees. This is the x-axis that has the degrees, theta in degrees, or pi radians. And I go 0, 0. 90 would give me 1. 180 would give me 0. 270 is going to give me negative 1. And 360 is going to give me that. So if you were to graph it, you are going to look like this. Okay, hold on, Armani. How come you're not just making a straight line? How come you're just making kind of a curvy thing? Well, the curvy thing is due to the values that you see here. There are some values that I did not talk about. I mean, we did talk about it when we walked around the unit circle, when we took a walk around the unit circle, if you guys remember. Like, for example, the half of 90 is 45, and it lives here somewhere. My graph is not drawn to scale, so half of the 90, let me go back one. Yeah, so something like here. And I believe some of you told me square root of 2 over 2, and I'm looking at the comments, 0.7. So I'm almost 0.7 here. See 0.7? 0.7. See that? That's why there's a curve. There's a curve here. And also, same thing, if you looked at 135, which is going to match the 107, 135 is going to be here, so this is 45, okay, which is going to be same length as this guy. So anyways, I'm not going to take too much time describing this, but you've got to know that there are some values here that make the lines curvy. It's not going to be a straight line. It will be a curve, because this is not linear here. This is not linear. It's not a straight line. You're definitely going to end up with a curve. Okay? And if you don't believe me, it's okay. Walk again around the unit circle, and you will find out that that's like the 0.86, for example, and 0.66, and the 0.7, etc., etc. There are some points. There are some more values. So when you graph them, you will end up with a curve that looks like this. What your eyes are beholding right now is the graph of the sine wave. That this is on the unit circle as points, but we said from the unit circle we came up with a table. We took the table and plotted what's on the table, with the x-axis having the value for the degrees, and in this case we had angle, like degrees, the angle in terms of degrees, not radians, but you still could have radians, obviously. And the y value is the value of the y value represents the y-axis represents the value for the function. So you plug in 0, you're going to get this amount, etc., etc. Okay, more on this to come. Okay, we're not done yet. So here is the question. And now, if you really, I have to fix this one. I'm not sure why this is coming up here. This is not, my apology, this is not the bottom here. This guy is actually just, this is 2 pi here. I'm not sure why is that coming up like this. I made a mistake. 2 pi, obviously. 360 is 2 pi. Okay, so this is 2 pi. Anyways, the point here is I'm trying to make is this is a table of all, I shouldn't say all values because that doesn't have all values, by the way. Some values. I have 0, I have 30, I have 45, 60, 90, 150, 180, etc., etc., etc. And you could see the points are 0.5, 0.7, 0.86, 0.5, negative 0.5, etc., etc. So if you were carefully graphing this, I bet you will end up with this graph here again. And this is the graph of the sine wave or sine function. That's how you graph it. It becomes like a wave. You start at 0, 0. Don't forget that. Sine starts at 0, 0. And then you're going to end up here with 360 or 2 pi. Okay, let's put some half of the 2 pi's halfway through. You're at 1 pi. And if you want to really be very facetious, I'm kidding. You could actually slice that in half. There's pi over 2 here. What about between pi and 2 pi over 3? Like between 180 and 2 and 360. Well, that's going to be 270. Come on. It's going to be here, which is 3 pi over 2. And you follow this circle, which gives you a table. The table gives you the graph. This is how you graph the sine function. Are we done? Almost. Because this is how you graph the parent function, the papa function, not the child. So the child could be like what you've seen in the warm-up, y equals x squared, and then you took that, and then you say, what? What do you mean? Well, I take that, and then I say, what if I wanted to shift left and right, up and down? What if the child is slower than the parent? Or what if the parent is shorter than the child? That's the idea of transformation. Oh, transformation. Talk to me about that. Transformation. Okay, before we talk about transformation, let's take a look at the sine function. The parent, this is the parent, and the parent has these characteristics here. The parents have these following characteristics. The first one is starting at 0, 0, go all the way to 1, if you guys remember, back to 0, and then to 2 pi would be here, okay? That's the sine wave. Remember, the least you can get for the parent is -1. That's the lowest. That's the bottom they can they can go down to. The top, how high can they jump, is all the way to 1, and that's it. They cannot jump higher. Up at the top with 1, down at the bottom with -1. Cannot go beyond 1, cannot go below -1. They can't. It's just limited. Okay. Now, what's the domain? What's the who? The x values. What's the domain? Okay, the domain is x values. What can you put for x's? What angles? They're asking you what angles can you put for x's. I could put 0. I could put, by the way, we put 30, 45, 60. Can I put 32? Oh, of course you could put 32. Can I put, let's say 35.97 as an angle? Yes, of course you could. Anything, any number could belong to the domain. Any number you would like, you could put for this domain. It's going to work. The range is the y-axis. How low can you go? How high can you reach? And if you could look here, the parent has the lowest value of -1. You can't exceed that. Has a maximum value of 1. You cannot go beyond that. They can't just go beyond that. The period. Once again, the period is how long does it take to start and finish that cycle. So the cycle, or the wave that I have here, if you guys looked closely at the wave, looked here, 0, all the way to 2 pi. See that? It's going to take all the way to 2 pi to finish the cycle, to finish the wave. From here to there is 2 pi's. That's the period. So the period is 2 pi's. For the sine parent, the period is 2 pi. How about the amplitude? We just said the amplitude, how high can you go? Well, remember the amplitude is always positive, okay? It's positive. So from this point, I'm going to erase and show you exactly what I mean by the amplitude. From the midpoint, right? Like if you're like on a bungee cord or something. How high can you jump? Up, parent, just 1. How low can you go down here? -1. Okay, so what's the distance here? Is 1. What's the distance up here? It's 1. That's what the amplitude is, okay? Away from the midpoint, how high can you go? How low can you reach, okay? It's 1 and it's 1. And what else? Is the amplitude is 1, we said, and the period is 2 pi. We've talked about the domain and we've talked about the range. And how do you graph the sine? Again, you start from 0, 0, go up to 1, down here, then go up to 2 pi. That's how you graph the sine wave. This is how you graph the parent sine wave, not the child. This is 1 here, remember, and at the bottom here there is a -1. Okay, this is a 1 at the top. This is bottom is -1. Okay, here's some good things about the children now. So the child could look like the parent, or it could not look like the parent. Okay. So first of all, let's take a look here. I am looking at a child that, for example, let's see here, the parent here says the parent is y equals a sine bx. The a here represents the vertical stretch or the compression. So how do you stretch? Well, you just like a rubber band. So take the rubber band and then you stretch it like this, up. Okay, up like this. How do you compress it? You compress it like this. Okay, you compress like this. So the compression and stretch depends on this A here, which will give you the amplitude, by the way. Like the amplitude, how high can you reach from the midpoint? How low can you go from the midpoint? That's going to be the A thing. Okay, and the second item here they want us to look at is the period. This B here helps you find the period. And I really need to make this clear. This is not the period itself. This here doesn't tell you how long does it take for this child to start and finish the wave. It doesn't. It helps you to find how long it takes for this child to start and finish the wave. Because the period is how long it takes. This B helps you find that period. It's not complicated. I'm going to just show you this right now. It's not really, it's very easy. Straightforward, it's not. So here we go. How do you find the A? I got some examples here. So let's find the A. It says, for example, you have I have a sine, so the amplitude is the absolute value of A, remember that? So it says here, what is the amplitude of this function? Y equals 3 sine x, okay, or f of x, by the way. So I'm going to start with this one, and I'm going to say, oh, okay, I think they're talking about this A. Yes, you were right, they're talking about this A. That's the amplitude. So the amplitude is the absolute value of A. What does that mean? Well, because remember, it's a distance. The amplitude is a distance, jumping distance, up or down. So it has to be positive. You can't walk like -2 miles to the mall. There's no such a thing. I can't travel -6 miles, or let's say -300 miles to LA or something. You can't travel negative. So distance has to be always positive. That's why I use the absolute value. So here, A is going to be, for our example here, A is going to be the absolute value. A is going to be the absolute value of 3, which is this item here, remember? This is A. which is just 3. A is 3. Well, how about the second example? Y equals negative 2 sine. You help me also guys in the comments. Y equals, don't wait for me until I solve it. If you could just get just a little bit ahead, do it. Y equals negative 2 sine, so A equals absolute value of negative 2. Well, it has to be 2. Come on, come on. This means that this child is actually twice as tall as the parent. Twice as tall as the parent. In this example here, twice as tall. So what about this negative? What does this negative do? Well, since you asked, I'm glad you asked. This negative actually just flips the wave. I'm going to sketch this one first. The top one here. So this goes to 3 is 1 and 2 and 3. Ooh, 1 and 2 and 3. Ooh, 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 down here. 3. Up here, 3. Okay, so this child, remember the parent only could reach to 1. Don't forget that. Sine by itself, the parent only reaches to 1 at the top and goes to negative 1 at the bottom. This child, however, is 3 times as tall. Oh my gosh, that's a lot of spaghetti there. 3 times as tall as the parent. Okay, and obviously it goes 3 times below as well. Nothing here about the period did not change. It does take the same amount for this guy to start and finish, which is 2 pi. Okay, the period is 2 pi for this dude. Meaning to start and finish, he took 360 degrees to start and finish the wave. Just like the parent. The only difference between him and the parent at this moment is this 3 here, which means he is 3 times as tall as the parent. How about this dude here? Well, we said 2, right? The amplitude is 2, which means I could go up to 2 here. If this is 1, this is 2. So I'm going to go up to 2 here and down to negative 2. So what's the difference here? Why is this negative here? I'm going to put a circle. What does this negative do here? This negative reflects. This negative reflects. Reflect over x. Reflect over x-axis. So instead of starting at the top here, this guy actually gonna flip. This guy's gonna start down here. If you paid close attention, the period did not change. It's 2 pi. The period did not change. All what this guy did is flipped, but the period did not change. Okay. Now, how about here? How about this child here? Well, this child says, I'm a little bit interesting because I'm different. Of course you're different. All of us are. This one says 3, which means now, remember the amplitude 3 times as tall. And this one says 2x. Okay, the 2 is the b. If you guys remember, the b helps me find the period. Helps me find how long this child takes to start and finish the wave. How long? So it does give you here a very important formula. I'm going to highlight that for you right now, just for you. I'm highlighting it for you right now. This one here. Oh, important. Oh, important. You find the period by putting 2 pi divided by the absolute value of that b. Be the change you want to see. Okay, so, for example, this guy here, I know the amplitude is 3. We're not discussing this at the moment. I'm looking at the b right now. So if I want to find the b, the period, I should say, the period is going to be, for me here, is going to be the 2 pi divided by this amount here, which is 2. Which means I'm going to end up with just a pi. Oh gosh. Yes, believe it or not, this guy here would finish the whole wave in 1 pi. Meaning, if this guy, for example, is helping his parent, maybe mow the lawn or something, and the parent, let's say, takes 2 hours to finish the job, this little guy here, of our friend here, says, you know what, Dad? I could finish it in 1 hour. I mean, I'm twice as fast as you are, basically, is what he's saying. Because if the parent only is 1x, but this guy's 2x's, twice as much, twice as fast. So if you were to graph this, if I were to graph this guy here, and this one says you are at the 1 and 2 and 3 at tall. Remember, this guy's 3 times as tall. And 1 and 2 and 3, -3 down here, 3 up here. Okay, that's long here. And it says I'm going to start and finish the whole thing. Remember? Oh my gosh. I'm going to start and finish the whole thing in 1 pi. What are you saying? I am saying that this endpoint is pi for the child. Twice as fast as the parent. Okay? And it actually is 3 times as tall as the parent because it goes all the way to 3 and down to -3 and all the way at the top to 3. Okay? Now, if this is a pi, remember this is the whole length here is pi because of the period. The b helped me find this period. And finally, you just have to know that if this is pi, half as much of your pi for that child has to be pi over 2. So at this location is pi over 2. And if you actually want to divide this further here, like divide the half into 2's, right, into halves, that's going to be pi over 4. And this guy's going to be 3 pi over 4, right? 3 pi over 4. Because 1/4, 2/4, 3/4, and then 4/4, which is the 1 pi. We talked about that in lecture 6, I believe. I'm going to put that in the link, description link, okay, for those who wanted to help with that. All right, the second one, or the last, I should say, on this side here. Let's go over it a little bit so we can see what we're talking about here. This one says, find what is the period of y equals 2 sine 6. Oh, 2 sine 6x. Talk to me about that. Okay, well, first thing first. 2 means the amplitude. I'm going to go all the way up to 2. And the 6 helps me find the period. How long does it take for this child to start and finish? Okay, sure. I could help you with that. Got no problem with that. I'm here for you. Woo! Okay, here we go. I'm going to do a little like this, and then we're going to go and just label things. This is 1, and this is 2. Approximately here, okay? -1 and -2. This is how high. Remember the how high? Depends on the amplitude here. So now how about the period? How long does it take for this child to start and finish? Well, the B could help you with that, by the way. I'm just saying. Okay, so the period is found by 2 pi divided by the absolute value of B. In my case, 2 pi divided by what? By the 6, which is, use your Fruit Ninja and chop chop. Read. I end up with a pi over 3. Pi over 3 is, how much is pi over 3, by the way? How much is pi over 3, guys, in the comments? Can you comment? Tell me, how much was pi over 3? Come on, you know that. Pi over 3. So this means this child starts and finishes the wave in pi over 3. Oh my gosh. It's like 6 times as fast as the parents. Are you serious? Yes. So if you were to graph this, if I were to graph it, I'm going to start here, go all the way up to 2, down here, all the way down to -2, and then up here again to 0. How long did it take me? Well, we just said this guy finishes the whole thing in pi over 3. Pi over 3 is here. Oh my gosh, like in 60 degrees. 60 degrees. Finish the whole thing in 60 degrees. So the parent would be just walking slow, and should be finished. Should be done by that amount of time. Well, all done a long time ago. The parents would be like here, dragging, but she's finished. She's sure. So if this is 60, half as much would be 30. And you get the drill, right? So half as much as this is 15, half as much as this. Between this is going to be 30, 45. It's going to be here, right? 45, 45, 15, etc., etc. Okay, that's how you deal with children. Okay, I'm going to finish with this example here. Okay. So it says stretching and compressing. Use sine x as f of x as equals sine x as the guide or the parent. Graph 1/2 sine, 1/2 x. Identify the amplitude and the period. Okay. Well, first thing first, I need to know the amplitude. Amplitude is the absolute value of this a here, right? I should say the amplitude is amplitude is going to be the absolute value of a, which is the absolute value of 1/2. Well, that means 1/2. But guess what? This guy is half as tall as the parent. No problem. How about the period? Well, the period is I know this formula for the period. 2 pi divided by the absolute value of b. Where is the b? B, the change you want to see. Here's the b. This is your b here. Remember? This is the b. Yep. And this is your a. This is your a. This is your b. So, okay. So back to the b. I'm going to say this is 2 pi divided by 1/2. Come on. Be courageous now. You have a fraction. Okay. So what? 2 pi divided by 1/2. You also could make this a fraction if you like. Make this a fraction. So you have 2 pi that doesn't change, times 2/1, which will give you a 4 pi divided by 1, or just 4 pi. Okay, so the period is 4 pi. The period is 4 pi. You could, right off the bat here, you could tell that this child is slower, obviously slower, right? Slower than the parent. And not just slower, but also shorter. Half as tall. And it takes 4 pi's for this child to finish the wave. Remember, the parent took them only 2 pi, 360, 2 pi. This guy needs 4 pi's. Like 360 plus another 360 just to finish the wave. And how does it look like? Well, let's just graph it. So I have my x-axis, which represents the angle. So now this child, if I were to graph this dude here, I'm going to start here. I'm going to go here, go down here, and go up here. I just have to know that this child reaches only 1/2, goes down to -1/2. This is -1/2. And let's just wrap this up. How long does it take for this child to start and finish? 4 pi's. Oh my gosh, 4 pi's. Very slow, like very slow. And half of this amount, half as much is going to be the 2 pi's. Half as much is going to be the 2 pi's here. And you could also just say this is 3 pi's here. And this is going to be just the 1 pi. 90, I said 180, 360, add another for these guys, and you find out these values. This guy, as we said, takes 4 pi's to start and finish. 4 pi's to start and finish. Next. So using f of x as sine x as guide or the parent, graph this here by telling us the amplitude and the period, and graph this guy here, sine again. I apologize. So at the top, basically you're using sine x to graph g of x, which is 1.5 sine of 2x's. 1.5 sine 2x's. Okay. You should end up with something that looks like this. All right. Last minute. Here we're gonna be, as always, 1 minute of Over with Armani, and this is the time where we not just discuss our feelings, because we don't discuss the feelings here, but we share hope. There is always hope. No matter what we're going through, there's always hope. As long as we have breath in our nostrils, there's always hope. We need a dosage, I think, a stimulus, let's say a stimulus package of faith and hope during these sort of times. And I believe God is providing this for us if we ask. So ask and you shall receive. We're going to ask for faith. We're going to ask for hope, for perseverance, for understanding for other people. And I believe God is going to give us that, because He is a compassionate God and He's always there for us. So now we're going to just be blessed and be thankful for what we have. I was eating a couple days ago, and I thought about people who are under the bridge, no food. They're just eating out of trash, basically. And people who don't have roofs on their head, top of their heads, and people who are in different places, and they eat some weird things because of the lack of money. But thank God that we have at least some food on the table. Okay, so we have hope as long as we are alive. Take care, guys. Love you all. Be blessed. Bye-bye.